Hi everyone, my name is Kuvina and welcome to a brand new series. The question in question today is how many regular polygons there are. This question is deceptively simple because although there are unambiguously infinitely many, there's still plenty of variation in regard to what gets included. In this video, we will examine various definitional ambiguity interpretations and see how that affects what counts towards the total, compiled together in a beautiful table, essentially the periodic table of polygons. As we refine our definition, we will encounter 5 specific nuances affecting the total. Be warned, things may get a little philosophical, but I'll do my best to remain unbiased and hear arguments on either side. And don't take anything too seriously. I really just want to show off some cool shapes. With that out of the way, let's begin. So what even is a polygon? Well, there isn't exactly an official definition, but nonetheless, there does exist an approximate mathematical consensus. A good starting point is something like an area of the plane bounded by straight lines. On screen are a bunch of examples that unambiguously fit the definition, but they're not all regular. For a polygon to be regular, it must have all sides the same length and all corners the same angle. Now, we're all familiar with regular squares, triangles, and hexagons with corresponding angles 90, 60, and 120 degrees. But how would you go about constructing a regular heptagon, for example? Well, there's a really useful formula for this. If you imagine starting on one edge and keeping track of your facing direction as you walk the perimeter, you will eventually complete one full 360-degree turn. This 360 degrees is the sum of the amount you turn at each corner. If all n corners have the same angle, each one will turn you 360 over n degrees. This corresponds to the exterior angle, or how far off from going straight you are. The interior angle is supplementary to this, making it 180 minus 360 over n. With that, we have a formula for the angles on a regular n-sided polygon. Sure enough, 3, 4, and 6 return the familiar angles. 5 returns 108, giving us a regular pentagon, and the rest follow similarly, with 7, 8, 9, and so on. We can represent these polygons with something called the Schläfli symbol. In this case, it's just a number in curly brackets. Essentially, whatever that number is, you input it into the angle formula, and then repeatedly connect line segments using that angle. Eventually, it will close up and you get a regular polygon with n sides, corresponding to the Schläfli symbol you started with. Executing this algorithm with all integers greater than or equal to 3 results in infinitely many regular polygons. With that, we've definitively answered how many there are, but there's still way more that can be added to this infinity. For example, what happens if we use a non-integer like 4.5? Does it give us a 4.5-sided shape? Well, if you input it into the formula, it returns 100 degrees exactly. If you try to build a shape with that angle, something interesting happens. By the 4th side, you've run out of room, but it hasn't linked up again, and doing so would destroy its regularity. But mathematicians don't give up so easily. If you're able to break through the barrier blocking the way, the existing edge, then it's possible to continue. After a second go around, you're in a similar situation as before, but this time, the remaining edge puts you exactly where you started. In total, the shape looped around twice while using 9 edges. This is known as the 9/2 enneagram, and it's no coincidence that 9/2 is 4.5. When looping around twice, you turn a total of 2 times 360 degrees. Distributing it across 9 corners, each one will turn you 360 times 2 over 9, which is equivalent to 360 divided by 9/2, aka the 4.5 we started with. In general, you could take any rational number and convert it to an irreducible fraction, a over b. And if you input it in the angle formula, what results is a shape with a sides that loops around b times. For example, 2.25 produces the 9/4 enneagram, 2.5 produces the 5/2 pentagram, and 2.4 makes the 12/5 dodecagram. These shapes are collectively known as polygrams. But are polygrams polygons? Well, this is where we encounter our first nuance, solidness. My definition from earlier makes reference to an area. Simple polygons have a very clear interior and exterior, but the same can't be said about polygrams, so making them fit that definition is tricky. However, not all definitions make reference to an area. As I mentioned earlier, there is no consensus, but compiling several major sources I found, we can see the essential components are that it must be a closed polygonal chain in the plane. A polygonal chain just means that point A connects to point B, which connects to point C, and so on using straight line segments. And for it to be closed, the last point also connects back to the first. With this definition, it's much more reasonable for the edges to go through each other, and so the polygrams count as polygons. But as the shapes get more abstract, the interior area still undoubtedly remains a useful concept, and is in some ways the defining characteristic of a polygon. So is there a way we could still apply it to polygrams? The answer is kind of. One technique is to consider the whole thing as one big interior. However, this leads to some of the boundaries separating interior from itself, and considering only those that actually bound the area, it becomes irregular. Another technique is binary shading, where every border separates interior from exterior in an alternating fashion. But my favorite technique is the concept of density. When building the polygram, you can imagine the edges having a direction, one side in and one side out. Whenever you cross a border into the shape, the density increases by 1, but crossing the other way decreases it. Using this technique, the 9-2 enneagram has a maximum density of 2 in the middle and 1 in the little triangles. In general, the maximum density is found in the center and equals the number of loops the gram does. So in the 9-4 enneagram, the center is essentially quadruple covered, which does kind of make a lot of sense. Anyway, since all rational numbers produce polygrams, we've successfully filled all the gaps between integers starting at 3. But why start at 3? What if we use a Schlafly symbol of 2? Well, the angle you get is 0 degrees, which just turns you around right back to where you started. The shape closes up, resulting in the two-sided diagon. But you'll notice its two edges have the exact same location. This is an example of our second nuance, degeneracy. And yes, that is an official mathematical term. To put it simply, a degenerate case is when the limiting case is qualitatively different than the rest. For example, you could define a quadrilateral using 4 points in the plane, and they can be moved continuously to get different quadrilaterals. But watch what happens when one of them is placed in the exact middle of the two surrounding it. The edges merge into a single edge and it turns triangular. But is it actually a triangle or a degenerate quadrilateral? And is there even a difference? This is the essence of degeneracy, indistinguishability. It also hints at a major philosophical question. Is it the definition that builds the shape, or the shape that necessitates a description? Judging by the simple geometry of it, it would be weird to call the shape anything other than a triangle. But if you define things more abstractly, then this is indeed the result of algorithmically building a closed polygonal chain from these 4 points. This is true of all nuances, but degeneracy especially exists on a continuum, and the diagon has a slightly worse case of it. Despite being anti-parallel directions, its two edges geometrically coincide exactly. Whether they can still remain distinct depends on your degeneracy tolerance, and if the algorithmic polygonal chain definition, which is what allowed polygrams, is enough to save it. What I'm going to do is assign each shape a degeneracy score from 0 to 4, which is invoked when aspects of your shape become indistinguishable. The diagon gets a 3, while the even more degenerate monogon and null polygon score 4. Degeneracy forms the basis of the periodic table of polygons, with the vertical axis representing our first nuance, solidness, with 3 tiers. Degeneracy can also run the other way. The opposite of a 0-degree angle would be 180 degrees. Solving for n, you get 1 over 0, which means you need infinitely many sides. In other words, it's the limiting case as you add sides. There are 2 ways to take this limit. You can keep sides the same length, or keep the area bounded. What results are 2 different realizations of the apeirogon, which I'm going to call bounded versus linear. They serve as a great introduction to our third main nuance, infinity. Some definitions explicitly forbid infinity, while some do it implicitly with words like bounded or variable names. In these cases, apeirogons are considered a separate entity to polygons, being their limiting case. But even without that, infinity can still cause issues, specifically in regard to forming a closed polygonal chain. The standard definition of closed is that your set of points has a first and last element which connect. But in the apeirogon, there is no last or first, and even if there were, they wouldn't connect. To make it work, you can redefine closed as simply not open. An open polygonal chain will have endpoints with only 1 line segment each, whereas on the apeirogons, every vertex has 2 line segments, so it doesn't exactly loop around, but it doesn't stop either. Even still, both forms of the apeirogon are degenerate in their own ways. The linear apeirogon is geometrically indistinguishable from a half plane, while the bounded apeirogon looks like a circle. And the angles being 180 is actually forbidden by Math World. So these will score 2 and 3, but they also introduce the infinity category. Alright, now let's return to polygrams. The introduction of degeneracy recontextualizes them somewhat because of the intersection points, but saving them from degeneracy and irregularity is still pretty easy, only requiring a bit of abstraction, so polygrams score 1. Now, even though there are infinitely many polygrams, we could still complete the collection, so to speak, by constraining the number of sides. With a numerator of 7, you have 3 choices for the denominator. 7 over 1 is just a standard regular heptagon, while 7 over 2 and 7 over 3 are 2 kinds of heptagrams. But is this really it for 7? Well, if you use 4, 5, or 6, you get negative angles, which result in the same shapes as before, just constructed in a different direction. 7 over 7 is the degenerate apeirogon, and other denominators are equivalent to adding multiples of 360 to the angle, leaving it unaffected. So for a given numerator a, the only denominators we need to consider are positive integers up to half of a. Let's try it with 9. 9 over 1 is the regular enneagon, and 9 over 2 and 9 over 4 are the aforementioned enneagrams. But we skip 9 over 3. If you input this in the formula, you get 60 degrees, just like a regular triangle. That's because 9 and 3 are not coprime. They share a factor in the form of 3, so this fraction is reducible and becomes 3, just like a triangle. But what if you still want a shape with 9 sides that loops around 3 times? Is it even possible? Well, in order to do so, you can reinterpret the algorithm as a multivariable function. There are 2 main ways to do this. The first is to use the same process but simply ignore the linkage until you make it to 9 sides. This results in the triply wound triangle, with several edges and vertices geometrically coinciding exactly. There's a whole family of these multiply wound polygons, but they're all degenerate, even more so than the diagon. The second approach is more complicated but also more useful. Take a look at the 10 to 3 decagram, for example. Just like the regular decagon, it has 10 evenly spaced corners, but instead of connecting adjacent corners, the edges connect corners spaced 3 apart. So an alternative algorithm could be something like this. To construct an A over B polygram, start with A evenly spaced points in a circle, and from each one, draw a line connecting it to the one B spaces clockwise. Using this method, the 9 over 3 enneagram looks like this. But if you look closely, you'll notice it's pretty much indistinguishable from 3 stacked triangles. This is an example of our fourth nuance, connectedness. You can somewhat connect the triangles with the idea of density from earlier, but even still, there are vertices that can't be reached from each other unless you're allowed to turn at corners that weren't designated as such. Due to this, it's almost always considered a regular compound rather than a regular polygon, which I don't disagree with. But there is still a nuance I think is at least worth mentioning. To see why, we'll briefly visit the third dimension. If you take a solid cube and dig a square hole in it, you get this. It's a polyhedron, which means it's made of polygons. But how many faces does it have? Counting them up, you'll probably get 10. 4 squares, 4 rectangles, and 2 of these things. Under the polygonal chain definition, this isn't a single polygon, since not all vertices connect via edges. But it's a bit weird to call it multiple shapes, and even weirder to do so with a polyhedron. In my opinion, solidness can actually be more relevant depending on context. And you can even relate it back to density by saying it's a compound of squares with density 1 and negative 1. In the context of answering how many regular polygons there are, things don't necessarily carry over in the same way. So what I'll do is put these compounds with the polygrams, but separated with an asterisk to represent disconnectedness. And of course, compounds can take many forms, not just triangles. In general, if A and B share a factor in common, which we'll call k, then A over B can be reduced by dividing both by k, and the corresponding Schläfli symbol is composed of k copies of that reduced form in a compound. For example, 10 over 2 is 2 pentagons, while 10 over 4 is 2 pentagrams, and 10 over 5 is 5 diagons. As a further example, here's the 12s. With this technique, we can fill in the gaps in our triangular table. And so, we've not only filled the continuous range of rational Schläfli symbols with polygrams, but with compounds, we've filled it multiple times. As for those before two, since angles are the same mod 360 and negatives make the same results, they just give us repeats. It still feels like something's missing though. A continuous range is not only filled with infinitely many rational numbers, but even more irrational ones. So that raises the question, can we have an irrational Schwarzschild symbol? The answer is maybe. Let's start with the most famous irrational number, pi. It obviously won't give us a shape with 3.14 sides, but what will it give us? Well, using the angle formula, we get about 65.408 degrees. It's pretty close to the 60 degrees of the equilateral triangle, which is why after 3 sides, it approximates a triangle. But it doesn't quite close up since you're a bit offset. This offset compounds upon itself until the 7th cycle, at which point the 22nd side puts you even closer. This time it approximates the 22/7 polygram, since 22/7 is close to pi. And the same thing keeps happening. As you fill in more of the shape, you eventually get closer and closer to the starting point, but never quite hit it. If you did, it would form a rational polygram with integers a/b, which would contradict the irrationality of n. So it seems like we're stuck, and it can't form a polygon because it never closes up. But the same was true of the apeirogon, so consider the limiting case. Infinitely many corners arranged in a circle, each of which joins 2 edges, which move you 1/pi of the way around the circle, and following the chain gets you to any other corner. This is yet another type of apeirogon. Unlike the others, it has non-degenerate angles, but although its edges have length, its symmetry group is continuous rather than discrete. This isn't an issue itself unless you specifically forbid non-discrete symmetries, but it does introduce a new type of degeneracy. Remember, the one we've been looking at was generated by pi, but there are infinitely many irrational polygrams, which can be seen by simply changing n continuously. Sometimes you hit a rational polygram along the way, but there are uncountably infinite variations of irrational ones, and even microscopic adjustments have significant effects. Some highlights include the phigon, egon, and taugon. Without the distinguishing colors, the only way to tell them apart is looking at where the edges stop. But without the abstract designation of these edges, they're all geometrically indistinguishable, resembling an infinitely dense circle. So the irrational polygrams ultimately score similarly to the other apeirogons, being degenerate but for different reasons. Alright, so that was pretty fun, but where can we go from here? Well, you might remember from earlier those negative angles that produce the same polygons as their positive counterparts, just constructed the other direction. Well, if the angles are truly equivalent, they should theoretically be interchangeable. So what would happen if we were to alternate between them? What results is this shape known as the zigzag apeirogon, and yes, that is an official mathematical term. But hold up a minute, if one side is considered the interior, then half of these angles are more accurately 240 degrees. And if that's allowed, then it would introduce shapes that really don't make sense to be called regular. So what gives? Well, it's about time we upgrade our definition again. Not the polygon part, this time it's the regularity part. The more technical way to define regularity involves transitivity. Edge transitive means you can map any edge onto any other while leaving the shape unchanged. For example, this edge can be brought over here with a rotation or here with a reflection, so the shape is edge transitive. Vertex transitive is similar, and here's a vertex transitive shape. Vertices and edges, as well as their higher dimensional equivalents, faces, cells, etc., are collectively known as elements. Being transitive in all your elements is necessary to be regular. But it's not sufficient. I actually got that wrong in tilings, so allow me to correct myself here. For a shape to be regular, it must be flag transitive, where a flag is a combination of mutually incident elements. For example, on the dodecahedron, this face-edge vertex combination is a flag. Polyhedra flags are often represented by triangles like this. And keep in mind, the color distinction is merely a visual aid and isn't present in the actual polyhedron. Since any flag can be mapped to any other without changing it, this dodecahedron is flag transitive and therefore regular. But with something like this rhombic tiling, for example, despite being vertex, edge, and face transitive, it's not flag transitive and therefore not regular. On a polygon, the flags look like this, basically half an edge. Everything we've added so far has been flag transitive, and transitivity also explains why regular compounds must overlap in very specific ways. The funky shapes with the 270s may have all edges the same length, but aren't edge transitive and therefore not flag transitive either. But what about the zigzag? Well, you can map any flag to any other using translations, rotations, reflections, and glide reflections. But in order to consider the shape unchanged, you have to completely sacrifice the idea of a solid area. If you choose to do so though, then the zigzag apeirogon is indeed flag transitive, and doesn't even have the degeneracy of the other apeirogons. I say the zigzag apeirogon, but actually there's more than one. Using different angles for the polygrams led to vastly different results, but with the zigzag apeirogon, all it does is change how pointy it is. These form a continuous infinite family, and the linear apeirogon is actually a degenerate case within this infinite family, to which you can optionally add an interior. But how do we represent these variations with the Schläfli symbol? I think it would make sense to put an apostrophe after the number to show that whatever angle you get, it alternates between negative and positive. But the conventional way is like this. The infinity represents the linear apeirogon, and the empty curly brackets represent a single line segment. The hashtag represents an operation called blending, which is a fancy way to combine shapes, but in this case, it's equivalent to zigzagification, where you raise half the points and lower the other half. With that, we have completed our table. The main section consists of simple polygons, rational polygrams, and reducible polygram compounds. The degenerate corner consists of the digon, monogon, and multiply wound polygons. And the infinite strip includes the bounded and linear apeirogon, as well as the infinite families of zigzags and irrational polygrams. Most of the entries are infinite families, some of which are uncountable. It's also possible to combine ideas, such as infinite winding or apeirogon compounds, but since the idea of including compounds was motivated by density, it makes less sense. Using this chart to answer how many regular polygons there are can be done however you want. Just as an example, I'll showcase my own personal reasoning. I consider apeirogons a separate entity to polygons because I don't think they count as closed. I also think an interior is kind of the defining characteristic of a polygon, either simply or with density. With a medium degeneracy tolerance, multiple winding is also excluded. This results in countably infinite simple polygons and polygrams, with compounds being the most natural extension of the idea. But of course, you don't have to do it like this. You might have completely different interpretations of the four nuances, which is perfectly fine as long as you're consistent. So feel free to use or modify the chart as much as you want. But hold up a minute. At the start I mentioned 5 nuances and this is only 4, so what's the final one? Well, most definitions clearly state polygons are 2D or plane figures. This implicitly and often explicitly means the flat Euclidean plane. But there are other types of two-dimensional geometries, for example spherical and hyperbolic. In the next episode, we'll take a look at how polygons change in these non-Euclidean geometries, as well as what happens when you lift the dimensional restrictions entirely. For now though, if you enjoyed watching colorful shapes, make sure to like and subscribe. Thank you for watching, and I'll see you next time. Bye!